Welcome to Hyperstition number 12, beaming power down from space with overview energy. And, I always say the number one ingredient we need for an abundant industrial civilization is energy, tons and tons of cheap energy. And as I think we rightfully recognize these days, all the energy in the solar system is in space. I mean, almost all the energy comes from the sun, and it's difficult to compete with that, this giant nuclear fusion ball in the sky. Now, another observation is that solar panels are becoming by far the cheapest per kilowatt hour source of energy, and they are getting cheaper at a extremely fast pace. So now we actually think, though, all the energy is in space, but all of our demand is on the Earth. So, how much industry can we put into space? Well, it's very difficult. If only there was a way to get all that space energy down onto the planet Earth. And now there's lots of ins and outs on how to do that. I mean, it's not easy. Do you need specialized terminals? Can you only do it during dawn and dusk? All these kinds of things. So a company that is solving this, and I think a very compelling manner in exactly the right way, is Overview Energy. And I have here the Mark Burt, the founder and CEO of Overview Energy. So I'm glad to have you here, man. How you doing?
Good. Sorry, it's Bertie. Sorry.
Bertie,
pronounce all the letters. Yeah, it's a super common mistake, but one I'm absolutely used to. So please don't feel bad about it. Everyone gets it wrong, actually. So, but yeah, Bertie.
Mark Bertie, awesome. So what is Overview Energy? What are you guys building? What's going on?
So, I mean, you hit the nail on the head there. One of the biggest problems on Earth is that we don't have energy where we want it. And that's, I think, the most important thing is it's in a lot of places, it's very easy to make it in various places. It's just where do you get it? And, the end state of that is, all the energy is in space, but all the demand currently is on the ground. And that's where
I know.
So yeah. What Overview is doing is we'll collect it in space, beam it down to the ground efficiently and safely, and so that we can utilize it everywhere we need it on Earth. And that's the long and short of it.
Okay. Now that idea has been around for a while, I think. I'm sure it's one of these things like that NASA researched in the 70s or something like that. But I think there's a lot of different ways of doing this. And I've always thought that there's a lot of different trade-offs in that. I mean, in my mind, it's kind of, the traditional things I've heard about is either it's a solar reflector, right? So you're bouncing light from space down to the Earth, or it's like the power station is on Earth, but then you use a microwave beam relay, but that microwave requires like a specialized ground terminal. And, the microwave is also kind of maybe a death ray in some way or something. So I'm curious, where have you guys kind of landed on this approach? Like, are you reflecting sunlight? Are you beaming down microwaves? Are you doing something else?
Yeah, something else. The differentiator for us lands into three things. It's wide beam, near infrared from geo is the easiest way to look at it. And I kind of, if you don't mind, like a quick go through those kind of one by one of why they're important. So when we talk wide beam, we talk, kilometer class. Okay, so our receivers are existing utility scale solar projects. So if you have a solar project that's a few hundred megawatts or bigger, it tends to be on the order of a kilometer or more across. That is our customer. Now, so we take solar energy converted in space from using PV, turn it into near infrared light and beam that down to the ground. The reason why near infrared is nothing can see it, nothing reacts negatively to it. It's absolutely safe, and it's the perfect wavelength to convert on solar panels. So like if you have a solar panel, normally under sunlight, it's like 20-25% efficient. Under near infrared light, it can be 50 to 60% efficient. And that fundamentally changes the calculus of that. And then it's in geo so that you see the sun all the time.
Is that using the standard mass produced commercial solar panels, or is that a specific band gap tuned panel that's adapted for this wavelength?
It's silicon. We have shorter wavelength versions that we're also exploring that'll work on cadmium telluride and things of that nature, but dominantly silicon is the best choice. The safest, lowest cost, most efficient laser assemblies that you can get and modify in our cases land in the wavelengths that are almost perfectly bandgap matched to silicon. It's actually quite fortuitous in that way.
Okay, awesome. And then is this also something like, does this work in only specific orbits? Does this work at certain times of the day? I'm guessing, does it make sense to only do this at night, or can you actually double up, continuously beam down 24 hours to a location?
Well, I mean, I think that was like 3 questions there. So like, I'll tease it apart. Okay.
With the orbital parameters here, because I'm curious, like where does it make sense to put this kind of, I guess, this energy generating asset?
So, and that was like the third pillar was geo. So this is geosynchronous, but not geostationary. And there is a fundamental difference that a lot of people sometimes can mix back and forth. Geostationary, if you don't mind the digression, is a specific subset of geosynchronous orbits. So geosynchronous orbits goes around once per day. So same orbital period as the Earth's rotational period. Geostationary is 0 inclination and 0 eccentricity, so perfectly circular. If you're in geostationary, you appear not to move relative to the background sky. Okay. Geosynchronous orbits, in our case, are slightly inclined and actually slightly elliptical. And that keeps us out of the belt where all the communication satellites are. So the satellite appears to trace an analemma in the sky, so figure 8 in the sky. And then when you put up a cluster of them, there are a bunch of kind of overlapping analemmas that are in this orbit. The advantage of that is, in this type of orbit, the satellite's illuminated by the sun I think it's like 99.2% of the time. So effectively all the time. And your ground site is now, whether it's sometimes during the day, sometimes during dusk, like as the satellite goes around, it's, whatever local time it is there. So we can deliver energy at night, which is when it's very useful, at peak times, morning and evening, which is, high cost times. But also if you wanted to, you could, as you said, double up during the day. And it's really like, where is the energy most useful? And I'm really want to, as we go through this conversation today, really kind of tease apart that's really the important thing, is not necessarily making energy at low cost, but getting it to where you need it to be at low cost.
Yeah, interesting. And I guess before we get into that, I'm curious still to kind of like have the top-down view here. Like,
okay.
Well, I guess, I mean, that is overview, right?
An overview of overview. Don't worry, the pun happens all the time.
Okay, we have this geosynchronous, not geostationary. We're using a infrared laser. It's really efficient with existing solar ground stations, and you're making this point. It's really about getting energy to where it's needed the most, kind of in real time. I guess the last question before we get into this is like, how is there a great deal of, I guess, atmospheric interference, sort of like cloud occlusion, like, this kind of stuff? I mean, do we lose a lot through the atmosphere?
So, that's actually a big complex question. So we'll kind of hit it top level first. Clouds do block near infrared. Okay, the atmosphere, it depends on your choice of wavelengths, but generally doesn't. There are atmospheric transmission windows that you can pick where water vapor or oxygen doesn't absorb the energy. And so you can minimize the absorption. However, clouds are scattered. They scatter the light out of the beam. Now, but if you think about it, if your receivers are large solar projects, okay, typically those are put in places where there's relatively few clouds. Like if you're in Southern California, it's cloudy, 20, 25% of the time, maybe 30%. And what's critical about this that you have to really think about is that it doesn't necessarily matter if a solar project that's one of your customers is necessarily cloudy at a given time. What matters is your utilization of the system as a whole. So let's say you're, hyperscaler or anyone, and you have solar projects in California and Texas. Okay. Well, it's very rarely cloudy in both places at the same time. So if it's cloudy at one, you send a beam to the other. And what you want to do is maximize the utilization of the power generating asset, the spacecraft. So yeah, clouds block it, but it turns out when you run the numbers and the economics and everything, that matters a lot less than people thought. In the past, people were like, oh, microwaves are great because they go through clouds and everything. And it's like, yeah, but there's all these other issues with that. And are clouds really the big deal that everyone kind of made them out to be? And it turns out the answer is no.
Yeah, from your perspective, there's so long as there's always a line of sight to some receivable target, to some power hungry customer, you guys are good.
Yeah, I prefer customer rather than target, but yeah, like
totally. Yeah. And I'm curious now to get into this topic of like this balancing energy grid demand, I guess, in real time using your steerable infrared laser. This is a very cool concept, I guess, actually, because normally we think, I mean, I know that's like the transmission infrastructure is actually one of the biggest bottlenecks to bringing new grid capacity online. And even if I mean, looking at like daily spot prices or hourly spot prices in California, there can be huge variances. in like, you know, a couple 100 miles, there's like massive swings in price just because it's so bottlenecked. So what's the dynamic, and is this key to like what you're selling into?
You're 100% right. Very good insight into that. Like, people think electric grids allow us to move energy or electricity across very long distances. And that's really not true. Like, yeah, it's all interconnected as a grid, but like in the US, the average distance electricity moves from generation to consumption is something like 100, 150 miles. Okay. So like you could put a huge power plant in Florida, but you're not using that electricity up in New York. And that's due to, you know, it takes a lot to build a transmission line, especially when you're talking about hundreds of megawatts, gigawatts. Just recently, there was a long transmission line that was supposed to go from somewhere in the Midwest, like in terms of Kansas, to move wind power to like Chicago, and it was canceled because it was really, really expensive. I usually joke that like a square mile of land is easy to buy unless it's 100 feet wide and 50 miles long. So like then it becomes very difficult. So if you can deliver the energy closer to where it needs to be or where the demand is, that fundamentally changes how you look at this, and it removes that kind of grid congestion aspect. And what we have found over the past like 5 to 10 years is the fastest generation to build is a solar project. You just need empty space, drop in the panels, there you go. Like, this is a reason why Meta is putting GPUs in tents next to a solar project. It's like getting the solar project's easy. It's the grid that's the hard part. So Overview can now, instead of that just being daytime power, it's now daytime, nighttime, peak times, etc. So you can drop solar projects in or already have them there and utilize them as now flexible sources of power.
Mm-hmm. And I'm curious, in your sort of I don't know if it's the mature constellation or sort of the target design point, like how much power is maybe one or the constellation total kind of delivering? I mean, maybe that's, you know, terawatts or something, but perhaps from the receiver point of view, is this like a 20% boost? Is this like a double? Is this, I mean, the sun is, I guess, 1,000 watts per square meter at the surface of the Earth.
Yeah. So, I mean, eventually we design the system to support, you know, 10 to 20% power of the planet. So we want to get to the terawatt level, and the design that you're kind of seeing in this graphic here, like, is designed to support that at scale. So this is what that looks like. This satellite here is, when fully deployed, it's a couple hundred meters tip to tip. But this is deployable, not assembled in space. You unfold it out of a, you know, more compacted object. This thing folded up fits inside a Falcon 9 shroud, so it's not even all that big. This is about a megawatt of equivalent electrical power on the Earth, so enough light to deliver that. To your question about, you know, what would a solar project get out of that? So let's see if I have a graphic on this. Okay, so like this is all the solar projects, and, you know, either currently existing or going to be online in the next couple of years that are 0.5 gigawatt or bigger. So this is like, you know, imagine these are all Overview customers. Those nameplate capacity is usually based on peak sunlight. So as you said, you know, 1,000 watts per square meter, whatever the maximum is. If you delivered 1,000 watt per square meter of Overview light, that would be absolutely safe. Okay. But you would now be converting that at 50 to 55% efficiency instead of 20 to 25. So you would actually be getting 2.5 times the peak power out. That said, now you need bigger inverters, bigger grid connections. So typically when we talk to customers, we're saying, look, we'll at the initial phase kind of put up enough satellites or deliver you enough light to match your nameplate capacity. So instead of you delivering 0.5 gigawatt noon and June in the Northern Hemisphere, you're delivering it all the time as long as there's not clouds. So your capacity factor, you know, which typically is, you know, it can be 25%, 35%, somewhere in there. So instead of making effectively 500 gigawatts 25% of the time, or 500 megawatts 25% of the time, you're now making it 70 to 80+% of the time. And that includes at night, evenings, etc.
That's huge. I mean, that's like a tripling. That's like or a little bit more of.
And that's without changing your grid. Because if you think about it, like, they're sizing the inverters and their grid connection for the peak. Like you have, like, if you're putting out 0.5 gigawatt, the grid connections has to be able to handle that 0.5 gigawatt. But if you make that 0.5 gigawatt all the time, you're getting, like you said, 2.5 times as much energy out of the system. Okay. Even though you haven't changed anything, like you haven't changed the solar project, you haven't changed inverters, you haven't changed your grid connection, it's all just there. So you're alleviating a lot of this grid congestion that is the problem. So you don't have to be in a new queue on this. You're just like, oh, okay, now it's just all the time. And that stability tends to make the grid easier, not harder.
I'm curious. I mean, on that point, can this actually lead to stabilization of these power swings and demand imbalances and that kind of stuff? I mean, is that because it's not this becomes in my mind like a very complicated algorithmic problem in some way. It's like you have these real-time energy fluctuations. Are you actively like targeting different spots to like always be selling where I guess the demand for that is the highest? You can always be selling at the highest marginal cost of energy as opposed to just this average cost.
Yeah, two things on that. The first one is like, yeah, you get to sell into that. Sorry, I kind of missed the first part of your question. To your second point, like where you want to be selling into the highest marginal price. The fortunate thing is that isn't actually a very hard real-time problem because it's already priced. So like you have a market. Okay.
Yeah,
so like if you pull up like gridstatus.io, like you can see what the real-time pricing is in various, in everywhere, and it's congestion and generation and everything associated with it. So if you think about it, what we kind of see as the potential end state of this is, imagine like right now we have real-time electricity spot markets, but they're very localized because you can't move power across huge distances very easily, like or near instantaneously. Now imagine if you had that kind of real-time market, but there's also a geographic aspect to it where, because it's untethered. So, you could be bidding on photons, like megawatt photon, and you could be bidding against a solar project in Portugal, and you could be a solar project in California. And we can let the market determine where is the best place for our photons in terms of who's going to pay that marginal rate. The advantage of that is now the market is actually looking to even that out. So the same type of arbitrage, where that price arbitrage, sorry to get into all the economics on it, but like that price arbitrage that drives people to put storage on the grid or put more flexibility on the grid or put in a new transmission line. On this, it's the same kind of that temporal arbitrage, but now there's also this geographic aspect to it where, you might have a huge amount of demand in one place and generation in the other, and you can't cross that without a huge amount of capital investment these days. You have to put in a transmission line. Whereas in our case, it's like, oh, okay, we need overview at 2 p.m. tomorrow because we're anticipating a big demand, and you're only paying for it when it's needed. So the grid will get better, and the average price of the electricity can go down on this by smoothing that out.
Yeah, you basically you're like trying to I think of like the stock market, like this the
ideally, yeah.
Like there's different bids for different quantities of energy, different prices. You can eat up starting at the top price, but that ends up bringing it down for everyone because you're kind of doing this like, I guess it's not peak shaving, that's more on the demand side, but peak supply addition. It's sort of
what's the opposite of it's demand shaving, supply
boosting? I don't know.
Boosting? Yeah. Yeah. And that's what batteries attempt to do. But batteries have the same issue as transmission lines and generation in that it doesn't move. Like if you build a fusion power plant at a city, it's in that energy market for the next however long the plant lasts, decades. Okay. Meaning that's your market. It's whatever that is instantaneously. Like if you talk to nuclear fission people way back, like, most of the time they make all their money in like January at night because nothing else is really working. So the rest of the time they're just, okay, well, we're making power. We're just going to keep the thing at 100% all the time and just pull the power out. But the profitable part is in January. Whereas with this, you're not building a power plant for any one market. You're building a power plant and then get to utilize it in all of the different markets that it can see. So like a satellite in GEO can see a third of the planet at a time. So you could think of it as, the satellite can see California in the morning, and then by the time the sun comes up in California, it's evening in Western Europe. You could switch the beam over there. The sun's gone down. Electricity is really expensive. Then by the time everyone goes to bed in Western Europe, it's now late afternoon, early evening in California. You can switch the beam back there. So you can treat this as, into the peaks. You can just power those, or you can power it all through the night, or any mix of that. And what's great is we don't have to change anything. Like you're just got solar project on the ground. We put our satellites up. The satellites are the same whether you're using it for peaking, whether you're using it at night, whether you're powering a data center, whether you're powering a city. It doesn't matter. It's the same thing. You now have the freedom to choose where and when you want it.
Mm-hmm, mm-hmm. And I think that is, like, in my mind, one of the most exciting things about this approach. I mean, the orbital mirror relay concept, I think, is Reflex Orbital. I think they're targeting just dawn dusk sails, basically, with a sun synchronous orbit, right? Which is more of a limited window. But their advantage over the microwave relay is it does not require a specialized ground station. I know that's always been the big barrier to microwave relay, like the economics, right? But now you guys can sell to any normal solar panel, and that's getting cheaper at like 20% per year, or the learning rate is like 20% per doubling of total capacity, and the capacity is completely exploding. So it's like, you're like, everyone wants to already build the ground station you're targeting. You know what I mean? And okay, so now I'm curious, how do we actually, produce tons of power in space, turn it into a laser, and then target the ground? I mean, that's...
Yeah, the devil's in the details. Yeah, you hit the nail on the head. That's the hard part. But that's also where, we just recently came out of stealth and with our airborne demonstration, and it's because we spent the last few years kind of solving that problem. You broke it down the right way. So you have to collect the energy, turn it into electricity, then supply that electricity, turn it into light of some fashion, get that to the ground, and that's a lot of tracking and pointing, and then convert it on the ground. And we have to attack every aspect of that. So let's go through them one by one. So you need to be able to get solar cells up in space. Okay. What matters there isn't necessarily their efficiency. It matters the cost. Okay. So how do you get the lowest cost over time integrated cells in space at as lowest cost as possible? And one of the things that people are realizing is, as launch costs are coming down, the actual best cells to put in space are actually just normal cells, because the cost of the cell itself starts mattering a lot more as the launch cost starts coming down. So right. This is why a lot of satellites are starting to switch to just terrestrial-like silicon cells instead of, multi-junction, very expensive cells, because terrestrial silicon cells, like as you mentioned, are getting so cheap. It's like tens of cents a watt. Whereas, triple junction 3.5 cells, you're looking at many dollars a watt, and they're only 30% instead of 20% in terms of efficiency. So it doesn't get that much better, but a lot more expensive. Then once you have that electricity, you have to convert it into, in this case, near infrared laser light. What's really crazy is that's a lot more efficient and lower cost than it was even 5-10 years ago. There's been such an uptick in demand for, laser diodes for welders or cutters and all different kinds of applications, LiDARs, that the cost of those have gone down dramatically, but also the efficiency has gone up a lot. Part of that was due to a defense program about 20 years ago, and that effectively doubled laser efficiencies over the course of a few years. But then also just consumer demand.
Is that Strategic Defense Initiative?
No, it was well after that. So SDI was like 80s. So do you mind a little story on it? It's actually a kind of a fun story. Okay.
Yeah, I love
okay, so I think it was in 2003. So basically DARPA is very far ahead. They're always like, okay, what's on the horizon? What's 10, 20 years out? And they're like, okay, lasers are going to be a thing. Like, we're going to have to shoot stuff down or whatever we need to do with it. So they came up with a program called Super High Efficiency Diode Sources, SHEDs. Okay. And their goal was like 85% efficient wall plug lasers. Okay, which is crazy. Like, if you think about it from an engineering perspective, turning electricity into something other than heat at 85% efficiency is really hard. And cut to the point is they actually did it. Okay, but there was some tweaks with it. So they did a bunch of physics stuff, a bunch of engineering stuff, and it got them up, I think, to like 70, 75, somewhere in there. Okay, and then the rest of it was, okay, well, let's cool the lasers down. Okay. And because, semiconductors get better when they're colder, you got less recombination, all different, stuff gets better from a physics perspective. And they're like, if we can get to like 85% at roughly about 0 degrees centigrade, it's worth it to refrigerate, like in terms of cost of the refrigeration and the energy you're using to move the heat. And that part failed. In order to get to like 85%, I think they needed to hit like minus 40 degrees centigrade or something like that. So that's why no one refrigerates lasers. Okay, even if it gets you a few more percentage points of efficiency. But let's say you had a spacecraft where one side always has to face the sun. Okay, well, the other side can be made pretty cold. So it's kind of this like, space as the ultimate heat sink that a lot of people say. But more importantly, think about it from the laser perspective. As the laser gets more efficient, you have less waste heat. That less waste heat means that your radiator is going to be colder, which makes your laser more efficient. And you get in this kind of positive design spiral. So lasers got dramatically more efficient, but only if you can make them really cold. And we can leverage that in terms of the spacecraft. And that actually gets us a lot of efficiency in there. So that was like something that very much changed. So now you have really efficient light coming out of the thing. Then you got to point it at the ground, and you have to do that at very high precision. And you have to do that at very low cost. And that's really what our recent demonstration was doing, was showing that we can point extremely high power, combined laser beams to a necessary customer to within the kind of precision we need from space, and do so from a moving platform, which was really the first of its kind.
Let's talk about that demonstration. What was going on there? I mean, was that with some airborne platform, or was that?
Yeah.
Okay.
I jumped ahead on you. Like, I'm just very excited about it. So,
yeah.
Oh, like, yeah. This was this was on our flight, one of our flights. You can see it kind of peeking out of the door. There's a Cessna Caravan. So in this case, we flew this aircraft at 16,500 feet, about 5,000 meter altitude. We flew it in a big circle. On the flight that you probably, if you look on our website, we have a video of it there. That flight, it was more of an egg than a circle. We had like 70 knot crosswinds, and the airplane's only flying 90 knots. So like the orbit is kind of like, and then you kind of do this kind of thing. So we flew that in a circle. The way the system works, and if you actually flip over, you can see a like GIF of the beam. So this is.
We should put that up there.
Yeah, sure. Why not? Yeah, this one. So this is an infrared camera. And what you're seeing is a looping GIF of a brief, like a very small couple of seconds of this test, where the beam is coming down and hitting actually a miniature solar project about 10, 15 meters across that we actually built at our test site. So what you don't see here is there's a beam that comes up from the ground, and then the system uses that to track it. So one beam is coming up from the ground that's saying, okay, here's where you need to put the beam. And then the high power beam comes down from the aircraft right to the solar panels on the ground. So you can go back to the presentation if you want.
Interesting.
Yeah.
So, is that, is that like also how you would design the satellite system, is having like this, I guess, pilot beam that's like, feed me. It's like a little, I'm thinking like some baby bird chirp, chirp, chirp. And then you just, you know what I mean? Like,
oh no, you're exactly right. Let's see if do I have a blow up of this? Yeah. So this takes advantage of the fact that optics are reciprocal. Okay. So if you think about it, like if I look at a mirror, and this is a camera, but let's say if you're two people standing in front of a mirror, okay, you look at the mirror, you see them, they look at the mirror, they see you. And those light paths are reciprocal. Like it goes the exact same path forward and backward. So if you have a beacon coming, we call it a beacon, coming up from the ground, okay, the satellite says, like, feed me little bird. But more importantly, if you tweak all your systems so that you're maximizing the receive of that, your beam going out follows the same path by definition, okay? So this is actually what we did in that airborne test, is in the middle of that solar project, there's a low power, very wide laser that illuminated the entire orbit of the aircraft. Okay. And I think by the time it gets to the airplane, it's like nanowatts or something like that. Okay. And then the optics on the airborne system track that and fire the beam back down the other way. So like one is getting bigger as it goes up and the other one is getting bigger as it goes down, and they kind of cross in the middle, and that's how we aim it. So one would imagine like all these different potential customers, you have this beacon in the middle of your solar project. And when you want the power, and all the different beacons are different coded and everything, you can be like, okay, well, we're beacon 1,582. Like we want 50 megawatts. And then, 50 satellites will then say, okay, beacon 15, whatever number, I don't remember what it was, and like send the beam to that direction. So it can work in that path, where again, all the satellites care is what beacon code they're looking for, and just maximize that, because they see the Earth isn't all that big viewed from geo. So like they can just pick this up. So all the complexity of where do I aim, how do I aim, all the precision, it's closed loop, but it's really simple because all you're trying to do is just maximize this return. So all the smarts are on the ground where it's easy to fix, easy to build, etc.
Yeah. Like I'm literally thinking like the control system is just like maximize my received power. That's all it has to do, right? Yeah, to point. I'm curious, like just in the weeds on that, like how, I'll get to the laser questions in a second, but for this pointing accuracy, like how sensitive or accurate does the pointing have to be? And is that like a solved problem, or is that easy or hard to do?
You're digging into the good stuff. I would say it's extremely hard, and we've solved it. So as like kind of spoiler alert. Okay, the way you have to think about it is what fraction of your beam spot do you need the beam to be stable over? Okay, so let's say your beam is, a kilometer or two across. Okay, well, you don't want that thing to wobble more than a tenth of the beam, 10 to 20% of the beam, because then you still have to fill that area with solar cells on the ground. And those are the edges of that aren't getting illuminated as brightly. So like ideally you want that kind of, think about it as like 10% of the beam spot is about what you want your, jitter to be. But the great thing about optics is the bigger your mirror, the smaller that beam spot. Okay, so it's somewhat of, I guess, an invariant. So like if you look at that video that we were showing where you have the beam coming down, okay, you saw the beam jittering around, but it was jittering around by about half of a beam spot. Okay, as you go farther away, the beam spot gets bigger, but the fraction that it's moving doesn't. Like if you think about it, if the beam say it's not a degree, but let's say the beam is a degree across and it's wobbling by half a degree. Well, it's still a degree across and wobbling by half a degree, whether it's 100 feet away or 200 feet away or 35,786 kilometers away. So what matters is for a given optical size, what is this fraction of beam diameter? Now, I called out two big numbers there. This test we just did in 70 knot winds on a turbulent aircraft, that was our first demonstration through this with I think that was our version 1 of the tracking algorithm, was 0.5. And we need it to be 0.1. So basically, first try from a turbulent airplane at 70 knot crosswinds, we were within a factor of 5 to where the thing sitting there quiescently in geosynchronous orbit needs to be in years, with probably a better tracking algorithm than we did for this one. So it's a really hard problem. But if you have the right team and the right ideas behind this, you can actually demonstrate that even at shorter ranges. So it's that kind of fractional spot that's really the thing you need to be looking at, and that's what we did.
Interesting. Yeah, this is very elegant. If you measure the beam jitter in terms of the spot size, it's an invariant regardless of distance.
Yep.
Yeah, that makes sense. I'm curious now on the laser tech. Is this? I'm guessing this is a CO2 laser as the gain medium. Oh,
no.
Sorry.
No. So it's diode. So it's semiconductor diode laser. The most efficient lasers you can get are that. Now, I want to be really clear that it's a fiber. In this case, we use fiber coupled diode laser. So shoot diode lasers into a fiber, and here, I'll look at the, if I pull this up. So on here, you have your solar. Can you see my mouse pointer? I don't know if
we cannot.
Okay, so the blue part's in the middle. You have this kind of solar array in the middle. Then there's this little fin sticking out behind it. That's where the lasers are. It's the radiator fin. That's black section along the back. So, and then we take all the light from those and bring it down into the middle where the optics are via fiber optics. So these are fiber coupled diode lasers, to difference from a fiber laser, which is where you have the same kind of thing, but then you have a specifically doped fiber that then takes that diode laser light and makes it much more narrow, both in frequency and in space. So if you have a laser welder, it's like a fiber laser, not a diode or fiber coupled diode laser. So the beam is very, very narrow in this case, but also less efficient. In this case, we rely on it to be way more efficient, even though the beam, by the time it hits the ground, is a kilometer across, 2 kilometers across.
And is this a large number of is this like a diode array where each one has kind of like a certain power output and they're all combining together into like this focusing optic output?
Yeah, I can get into that a little bit before I'll start hitting some proprietary stuff. So,
Sure.
in effect, like diodes are typically for an individual emitter watts to tens of watts. Okay, so you take a bunch of diodes and you direct it into a fiber. Okay, so now you're at hundreds of watts to thousands of watts. And then you take those fibers and then you can do some beam combining stuff in order to then direct those out the telescope, basically, down to the ground. So if you think about, say a diode is 20 watts. Well, if it's 2 megawatts, you have 100,000 diodes. You have going into thousands of fibers, going into tens to hundreds of telescopes on the spacecraft.
Mm-hmm, mm-hmm. I mean, I'm curious too, because so solar panels, I guess, are more resilient. I would think laser diodes might be more sensitive. You're in geosync orbit. This is like far outside the Earth's Van Allen belts, which are like magnetic shielding. Is there a concern about this, like ionization, radiation, degradation? Is that a significant system design consideration?
Oh, it's a huge consideration. I'll treat the two as the two separate things. So there's the diode effects and then there's the solar panel effects. Remember I mentioned earlier that on the solar panels, like everyone's kind of going to using silicon in space. Okay, now silicon in space gets hammered by radiation a lot more than like thin film triple junction cells. So the thing you have to think about is, do you care? Okay, remember, because it all comes down to cost. Okay, yeah. Like if the cell is, so like take a silicon solar cell. Okay, it's 25% efficient, ballpark. Okay, I hit it with a crap load of radiation. It'll knock it down. It might end up being, let's say, 10 to 12% efficient at the end of a huge amount of radiation dose. Okay, well, that means that the average for that cell is about 15% from beginning of life to end of life. Well, okay, the triple junction cell might go from 30% to 28% over the same time. Okay, so one's 29 average and one's 15 average. But the silicon cell is 10 cents a watt up front and the other cell is like $70 a watt up front. So what matters really is, including launch costs and everything else, like is the kind of dollars per, I guess, net present value integrated energy delivered better. Okay, so on the cells, like for instance, we use relatively low cost terrestrial cells is what we're baselining for this. Now, like there's tons of advanced cells being developed and like we have LOIs with many like advanced cell companies. Like if someone can make a super efficient, very lightweight cell for cheap, oh yeah, give me a call. Like we'll definitely talk to you on that one. And we're agnostic to the actual type of cell. So, but the radiation thing, like, yeah, it degrades, but economically, does that matter if the cell is cheap enough? Okay, and the launch cost cheap enough. On the lasers, well, that's a more important thing to think about. But like the really thing to think about is how much area actually is there? Like solar cells, okay, so in space you might be getting a couple hundred watts per square meter. So say 200 watts out of a square meter of solar panel, okay? And it's very thin and lightweight. Each of those laser diodes that I mentioned, they're about like 20 watts or something like that. That diode is about 3 millimeters square. Okay, so that means you could fit 90,000 of them in a square meter, meaning a square meter of laser diodes is 1.8 megawatts. Okay, so a couple of megawatts worth of laser in space, it's about a square meter, meaning you can put an inch of aluminum on top of it if you need to shield it.
Yeah.
And not really, you've added, 150 pounds to the satellite. Like, again, one of my guys always jokes that Overview was started by a techno-economic analysis. And I'm like, well, you're not entirely wrong. Like, engineering's all about achieving the goal with the right price for the right market, with the right technology and safety and everything else. So it's a great set of questions because, and unfortunately, kind of the answer is, does it matter actually? Like, is it really, like, the question you're asking is like, can you deal with the cost of that impact? And the answer is
right. Yeah. And I mean, that's what's cool and fun about this is that it's like the more we master physics, the better our economic levers get, right? Like these high efficient diode lasers, super efficient cheap panels, cheaper launch costs. This niche just kind of explodes. It comes out of nowhere, and now you have like a steerable But basically, it's like this dispatchable, spatially distributed power station, solar power station.
We use the term geographically untethered.
Yeah,
Of where it goes. I'm really glad you pointed out kind of like all these different things. It's one of these things where it's like the best kind of engineering is where the same solution solves more than one problem.
Yes.
Okay.
This is the elegance.
Yeah. There's I'm a big science fiction fan. Like, so Larry Niven wrote a book called The Mode in God's Eye, and it has these aliens in it where they're so good at engineering that they'll make one thing do 5 different things simultaneously. And then another thing will do 3 of those things and another 2 things because they're so good at it. So there's so many things about Overview where it's like, oh, okay, well, if we solve this problem this way, it also solves this. I'll give you a good example. So like one of the ways you achieve what we call passive safety for this, which is you don't have to turn it off if something gets in the beam. It's just you can stand in there, you can stare at it. It's 100% eye safe. It's all inside existing regulations. Like you can just literally just stand there and stare at it. One of the ways we do that is by having lots of satellites. Okay, so each satellite's about a megawatt. Let's say you have a 500 megawatt solar farm. So you need to have 500 satellites. Well, what that means is each individual satellite is only delivering 1/500th of the power. So the reason why lasers you have to worry about your eyes is like it's coming from one point source. So if you think about it, a couple milliwatt laser pointer can be very dangerous in your eye, but you can stick your eye up to like a 100-watt light bulb and be totally fine because it's this huge angular area. It's an extended source. So by having a bunch of satellites shining down, it means that the light is now an extended source, and that's what makes it safe. The good thing is, by breaking it up into individual satellites, it means you don't have to assemble them in space anymore. You can just unfold them out of the launch vehicle, so you don't need an on-orbit robot or anything like that. So the same solution, and also makes you resilient. Like, say one breaks, well, you've only lost 1/500th of them. It's kind of the Starlink thing where it's like, oh no, we lost the satellite.
Yeah.
So the same solution solves your resilience problem, your safety problem, and the need for on-orbit assembly. It eliminates it. So by picking one thing, it actually makes it easier to do multiple things. And there's so many aspects of Overview where that kind of, group solve thing happens. And that's
like another one comes to mind, which is this pointing accuracy versus beam size versus size of solar station on the ground. Like because if your beam is 1 kilometer across and that's smaller than the size of the solar array field or something, and I'm assuming there's like a linearity of solar panel response to additional energy, like you're not saturating that limit in some way. You can like all of the power will be absorbed, even if you had jitter or whatever, right? Is this true?
I mean, it is nonlinear. Actually, usually I don't think of it that way. We just try and minimize the jitter because if you think about it, if it's at night, if like it jitters off the spot, those solar panels, they have an inverter on it. So that inverter will go from needing to synchronize and starting up. So like you don't want to like turn it on and off. So like we generally just look at the non-jittery part as the power generating part, and that like penumbra, I guess, like around that of being a loss factor to it. To your point though, in terms of like solving the same thing, a lot of different ways, is one of the early realizations with Overview was actually that the lasers that we're using, by making them fiber coupled instead of a fiber laser, the beam quality, basically the angular width of the laser coming out, is a lot broader. Like people will talk like, times diffraction limit or something like that. So like a fiber laser, you can get to be basically diffraction limited. So you're limited by just the size of the thing. A typical fiber coupled like diode laser is going to be somewhere between 20 and 50 times that. So the beam is 20 to 50 times bigger, but it'll be 70 to 80% efficient instead of 40% efficient. And it'll be half the cost or even less. Okay. So when I was first coming up with this, I was like, yeah, but then then you need kilometers across of receiver covered in silicon. Wait, we have that. Like they're called solar projects. So that was like the core piece of it where it's like, oh crap, like someone already built the receiver. The best receiver is silicon. We're covering square kilometers with silicon. Like it's already there. So the fact that it's, remember earlier I said, like, wide beam near infrared from geo, the wide beam doesn't hurt you. It only hurts you that you need a bigger receiver. But if someone's already built it, that wide beam doesn't cost you anything. And in fact makes all the other aspects of it easier and cheaper.
I'm curious. I want to start asking about like satellite deployment and manufacturing stuff. But before that, just one last sort of on the techno-economic front. Is there like a kind of an order of magnitude estimate of like, if we call the addressable market you're selling into like stranded solar in some sense, it's like underutilized solar or something like that. Like how many latent gigawatts can we be supplying, I guess?
So, I mean, global solar capacity, I don't have the number right off the top of my head, but let's say, I think it's a few hundred gigawatts at this point. Okay. So the average capacity factor, I'm just going to spitball and say it's about 25%. Okay. It's in a lot of cases it's higher, but in like, the winter, it's going to be a lot less if it's a temporal zone. So let's just say global average. And I know one of my guys is going to like yell at me and be like, you should have this number off the top of your head. But let's just say it's, to make the math easier, 400 gigawatts. Okay. That means that 400 gigawatts of installed peak solar is on average making 100 gigawatts. Just average. Okay. With this, now you're looking at, that could easily be 75, 80% capacity factor. So that means that you went from 100 gigawatts average to now 300 gigawatts average. So right there, you're looking at an appreciable fraction of the average power of humanity. And that's just the solar projects you already have, not to mention new ones.
All the new deployment. So basically, if you wanted to think like, what's the energy impact of the geosync, near infrared, laser diode approach? It's basically just 2 to 3x the total solar generated capacity currently. Like that's the upper boundary. Yeah. But just that continues to be true into the future. Like,
yeah. We actually did a couple of analyses just recently where I'm actually take for instance, I think we did an analysis recently for Saudi Arabia, and I think they're installing something like 100 to 130 gigawatts of solar power. If that was utilized with Overview, that would be all of the electrical power of Saudi Arabia. Just what they're already putting in, just illuminated by Overview, because now you're at 24/7. I did an analysis once where for Australia, you could power all of Australia with a solar project less than 15 kilometers square, like 15 kilometers on a side, and that's all of Australia. And so like you start fundamentally changing the areas required, but this scales to Earth. Do you mind like a 30-second, like kind of how I think about this or kind of why I got it, why this? We need to basically double or triple the electrical power of the planet in the next 25 years. Okay. It would be really nice if that was done in an environmentally conscious way along the way. Like, we're not going to rewind and do it with coal. Okay. So there's really only 5 ways to do it. Okay. That scale to planetary levels. It's fission, fusion, terrestrial solar plus storage, advanced geothermal, and space solar energy. That's it. Those are the only things that you can be like, you can say like, okay, this scales to terawatts, but they all have individual difficulties and that are different types. So like fission has political issues, potential waste issues, and bear in mind, I'm a nuclear engineer. So like, you can get there, but it's a road. And in a lot of cases, it isn't engineering. Okay. Fusion has a lot of engineering issues plus manufacturing scale, and there's a huge amount of unbelievably great companies, some of which I actually work with as a consultant and as an advisor, and they'll get there, okay? But again, like the fusion plant doesn't move. Like wherever you build it, it's there, and that's your market. Terrestrial solar plus storage, the issue there is it takes up a lot of space, okay? Because on average, it's only being used effectively 25% of the time. So I saw one thing where they're like, oh yeah, it's an area about the equivalent of like half of Arizona to, do all the energy needs of the United States. And I'm like, okay, well, Arizona's really pretty. I like going there. Like, let's not cover that with, solar farms. But if you can reduce that by, a factor of 10, Now you can distribute it out, because if you think about it, remember, we don't care about latitude. Like, you can be as far north as you want. So you could put a solar project, by Chicago and have it work as effectively as one in Southern California. So now you can put it a lot more local. So space solar energy is the big solve on that. And it works with the mix of these things, because now, the geographically untethered part, you put it where you need it to be.
Mm-hmm, mm-hmm. That's a really good argument. I had not thought of that. I mean, and that is the criticism of solar when you see this like stack ranked nuclear. It's land footprint, but it's also materials consumption through rate, right? Which is like in terms of aluminum and steel and concrete and like copper and silver. And so if you can triple the amount of power produced by a given solar facility, yeah, I mean, it's less land, it's less materials, for a given thing, and you can put them more places. All this you don't need as many. Like the battery installation has its own big material costs in terms of like lithium and other minerals, that kind of stuff. Yeah, so I get it. This is really cool. Okay. So I'm sold on the diode near infrared geosync economic argument and the technology. Let's okay. Now we're launching rockets. We're launching rockets and we're deploying satellites into space. I mean, do these have to be like megastructure size? Is the deployment a big issue? Like, where do these rank up in the kind of like engineering technical risk?
Okay, so you hit the nail on the head. Okay, so if you asked me a year ago, like, what is the thing that keeps you up at night? Or ask like my VP Space Systems, who's a deployables guy. And it's like, if you asked us a year ago, like, what keeps you up at night? We both would have said like, oh, deployment. Because unfolding stuff in space. So first of all, this isn't a megastructure. Like the thing I'm showing here, tip to tip, this is like 200 meters. Okay, each one of those things like Z folds down and folds up. This fits in a Falcon 9 shroud, or a bunch of them in a Starship, or a bunch in a New Glenn. Like, we're designing it to be launch vehicle agnostic as long as it's cheap. Okay, so we would have said deployment. Now, no. Okay, so one thing, and actually this patent was just recently allowed, we have the highest packing density folding truss that's ever been tested in 0G or deployed. It's like 4 to 10 times better than anything else out there. And critically, it's extremely reliable, very rigid, and allows us to do this kind of 100-meter deployment on this. And we've tested that at subscale in a 0G flight. I think I actually sent you the video. You want to pop that up? This is us, 0G. Aurelia Institute put this together for one of their portfolio companies. And this is actually us testing one element of the deployment. So there you saw that thing pop out. So that right there, it loops, so you can put it back. I'm there on the left. If you notice, I'm having a lot of fun in 0G standing. So yeah, I showed this video to my wife. She's like, "You're not floating around." I'm like, "I'm working. Like, what do you expect?" Like, sorry. But yeah, so that truss has a surface area to volume ratio of like 250, meaning you could put 250 square meters, and at that scale. If you scale that up by a factor of 10, those struts get about 2.5 times bigger. Mm-hmm. So it actually gets better by about a factor of 4. So now you're at close to 1,000 square meters per cubic meter. Nothing comes close. This truss on that thing, on that size where it's 100 meters, would have the same like bending frequency as the ISS, while having its truss be about 100x lighter. So these are fundamental breakthroughs. So now we actually just had an investor ask my VP Space Systems the same thing. He's like, "Well, what keeps you up at night?" And he just said, "I sleep pretty well." I was like, dude, like, chill a second there. Awesome. But yeah, so deploying stuff in space is hard. Like, that is the critical things. Our next step on this is to do this subscale demonstration in LEO. We have a SpaceX launch for, I think, January 28th booked for that. And so, like, we're, crawl, walk, run, like, but these are all integrated tests. So yeah, putting it up in space, that's going to be the hard part. But it's also something that people are solving. Like, if you think about it, look at how much Starlink SpaceX put up in the past just few years. Like, space is changing a lot, and this is the kind of thing that can take advantage of that.
Mm-hmm, mm-hmm. And then I'm trying to think of the other sort of things that would come to mind in terms of space systems. I would guess that if you have like a megawatt-ish of laser diodes in a square meter, even running at pretty high efficiency, that's still a lot of heat to dump to space. So I mean, is the radiator design here like another big challenge, or is it like relative to its size also like pretty approachable?
Well, remember that all the laser diodes aren't in one place.
Ah.
Okay, so they're spread out on that. Like if you can kind of, I guess you can't really zoom in on this, but like there's that little black strip. Oh, there we go. Like that little black strip, that's the extended radiator. So on this type of system, the laser modules are spread out along that strip that folds up along with the solar panel. And then all the light is brought to the middle of that satellite by the fiber optics. So what that does is it disperses the heat out, across this much larger area and makes that a lot easier to accommodate. So it isn't you have this kind of dense thermal core. Like, I mean, one of the things that people talk about is like on orbital data centers, and there's a huge heat problem with that because you want all of your compute in this like little tiny thing, but then you have to get the heat everywhere else, and that's the hard problem. It isn't that the eventual heat sink is the problem. It's, how do I get a megawatt of heat from this thing the size of a 55-gallon drum and spread it out over hundreds and hundreds and hundreds of square meters? In this case, because each laser module is about yay big and makes a few hundred watts, you only have to spread that thing's heat over about a square meter. So the heat only has to go 20 inches, 50 centimeters, instead of having to go many tens of meters. Because again, like we can shield the little tiny laser diodes efficiently, and we bring all that light down into the middle with very lightweight, space qualified fiber optics. So it's kind of the opposite problem and a much easier solution than the really hard part of data centers, which is the thermal management.
But you don't need any heat pump circulating fluid or anything like that. It's all.
We use heat pipes, which is kind of what's in your laptop. So it's just, metal tube full of, in this case, you use typically ammonia, or in your laptop uses water. But it's as close to a passive heat thing as possible. It's a metal tube full of liquid. And, these are flown in space tens and tens of thousands of times. So, but since you're only moving it over like 20 inches and that thing can be rigid, so no bending or anything like that, it makes it a fundamentally easier thermal problem.
Mm-hmm. One thing I would think too, though, so you are in geosync orbit, but you're always, to get your 95% power, effective power capacity, you have to be constantly reorienting the panels towards the sun. Do you not?
Yeah. So the way this works is, so there's that satellite. You can think of it as like two big wings and what we call the center body. So those wings have to be always facing the sun. So as it goes around the Earth, like imagine the camera is the sun and the Earth is somewhere in the middle here. So the satellite always has to be facing the sun. Okay. The way we do that is it's actually passively stable. So that little part in the middle with all the telescopes, there's a lot of mass there. So the center of solar pressure is actually behind the center of mass. So it's like a parachute almost. And even the small amount of momentum from the sunlight hitting it, that force, like always centers it. So that always keeps it where it's always facing the sun. That middle part has to rotate once every 24 hours as it goes around the Earth to keep the beam directed at the Earth. Now, rotating things in space is always hard. Okay. It's like, you don't want to put stuff across a rotary joint, whether it's power, light, fluids, anything like that. So one of the key things that we actually developed is in the middle, you have these kind of two mirrors like this, and the light actually comes to these parts that don't rotate. And only that mirror in the middle that redirects the power to the ground, that is the only thing that rotates. So what you've done is you've now made it where nothing has to cross this rotary boundary, and that really gives you the kind of long-term reliability that you need and makes the system much simpler. So you're kind of collecting it here, bringing it down to the middle, and then now you're directing it at the ground. So that's what maintains it in that kind of orientation.
That's really interesting. So, okay, so you are not necessarily constantly burning like any kind of like propellant or torquing up reaction wheels to maintain what you'd think of as steady state operation. That would just be for small corrections and such.
Yeah, and even then, so it's, Okay. I got into space stuff and nuclear stuff because it's like when you're working at like the edge of energy densities and stuff, like things get really cool. So I'll give you kind of two real quick ones. Remember where I said like this it's actually is relevant. So remember where I said the optical fiber is like it's a couple hundred microns across, and you're putting 1,000 watts through that fiber. Well, that means that the power density in that fiber is something like 50 to 100 gigawatts per square meter. That's about 0.1 psi of light pressure. Like it's actually like a macroscopic amount of light pressure in the optical fiber. So like dealing with that, you have to be careful. Okay. But a megawatt of light is about 3 millinewtons. So just the laser beam leaving the satellite is actually a minor amount of thrust. Like over the course of a year, I think it works out to like a few tens of meters per second of effective delta V just from the laser beam. So, and you can, because it's offset from the overall center mass of the vehicle, like it means that you can actually get some propulsiveness from the laser, depending upon where you direct it. The other thing is the solar pressure hitting the thing itself is a significant amount of force. So we actually have filed IP on this where by changing the orientation of the spacecraft or changing its cross-sectional area, you can maneuver the spacecraft as well. And other people have done that. We do it in a different way. But you can use those kinds of things once you get into these kind of large area type structures, like a solar sail. It's not that light per unit area, but you can still have effects. The nice thing about GEO is stuff doesn't happen all that fast, and you don't need a lot of delta V to move yourself around and do any of those kinds of things. So we don't really have any active systems in order to do the kind of orbital maneuvering and orientation that one would normally need.
I mean, that's a huge deal, right? Because often that's the limiting factor on satellite like lifetime operability is like you run out of maneuvering or attitude control propellant or RPM when your torque reaction wheels or something, right? So it's like eventually it just. So I'm curious then. I definitely get this. This is very elegant design. Like there's the same things keep solving problems. Very Modi engineering code.
Yeah. So yeah, the same thing is like, satellites have to, when they're very dense, they don't have a lot of sunlight hitting them. And in fact, like, satellite designers have to worry about solar pressure. Like, like if you have one solar ray sticking out on one side and nothing out of the other side, it'll actually turn it. Okay. So they have to compensate for this. So everyone has to deal with this, and solar sails leverage this. And if you're in between, it's the sun doesn't hit you enough where you have to, in this case, worry, like somehow keep it from pushing you out of orbit, but you can use it for the kind of limited maneuverability you need. So, by making it light enough to be economical to put up, you're also moving it into the regime where now you can use that to your advantage. So yeah, it's very Modi. Hopefully a significant fraction of your audience will like get that reference, or at least hopefully read the book. But yeah, it's a great way to put it.
Yeah. Well, it's a great book. I highly encourage it. And so you are not as limited as onboard propellant or station keeping fuel. You're way out of the atmosphere, so there's no appreciable drag, anything like that. So really the limiting factor on the satellite lifetime probably is just this like high ionization radiation damage, I would guess.
Well, you have to treat kind of reliability and degradation as two separate things when you're looking at this. And again, economics rears its ugly head. If the system is still working, but produces steadily less power, it's still generating revenue. It's only if something takes out that bird that you lose that megawatt or that whole megawatt. So like, let's say you put one of these up, and again, these are all hypothetical numbers. So like, let's say you put one of these up, and at the beginning of life, it's making a megawatt. And after 20 years, it's making half that. Okay. Well, but if it's something on it fundamentally breaks, you lose the whole half megawatt right whenever it happens. So we have to treat from an engineering perspective, like at what rate does it degrade versus when does it fail? Okay. So again, remember I mentioned that rotary part in the middle. That's really the single point failure mode, where like if it can no longer we call it the lighthouse. If it can no longer lighthouse around to track the Earth, you're done. Like that satellite doesn't work anymore. Again, Modi engineering, you're putting up hundreds of these things. So like You lost one. Oh, well, 1 megawatt out of the 50 gigawatts. Oh, well, put up another one. We're constantly putting these things up. So, but that's now we can take engineering into account of that. So you can now have that with multiple redundant drives, or, how do you make it so that if a motor seizes, it doesn't fail locked? Like, there's a bunch of different engineering you can do to say, like, okay, the drive, because you don't want a 1% failure chance per year, because that'll, over 20 years, that's a lot. So it's like, how do you make it so that it's, in effect, like, by the time something fails, it's degraded enough where it's not as useful anymore. And you have to balance those things, again, from an economics perspective. I'm sorry to keep coming back to economics, but
it's everything.
This is energy. Like, it's dollars per megawatt hour. It's, over time. Those are all the decisions. It doesn't matter how cool or slick or anything like that is. It just matters, like, are you safe? Can you produce the power? Can you produce it at the kind of cost that's reasonable?
Interesting. Now, is in my sort of now more sci-fi minded vision of the future, is there other like applications we could think about for this? Like, I don't know, I'm planning a wedding and I want it to be like 2 degrees warmer or something. Like, can I give you a phone call and call in some?
You would have to pay a lot. Okay. So we've actually get this question quite a bit. People, everything from, does it, if a vineyard is going to get a frost, can you that was actually a really clever question where I was like, oh, I never thought of the economic impact of that. It turns out warming things requires a lot of power. Okay. So think about it, sunlight, as you mentioned, is 1,000 watts per square meter. And think about say you're on a ski hill in the middle of winter. Okay. You're getting a double dose of sunlight. It's not that much warmer. Like, you need a lot of sunlight before you can appreciably change the surface temperature of stuff. Now, over the course of the day, that's true. Okay. But you can still have direct sunlight hitting something and have it be relatively cold if the ambient air is cold. Okay. Because convection dominates over the absorption at the kind of temperatures that we exist at. So you would have to put not only our peak is only, half a sunlight to sunlight. You can have all the sunlight you want on a cold day. It's not going to be that much warmer. Right. And this is also, the beam is kilometers across. So let's say you wanted sunlight over a few square kilometers. You're talking gigawatts of power. $50 a megawatt hour, a gigawatt's $50,000 an hour. So you would have to pay an enormous amount of money for that. And also remember that we have to track a beacon. So one of the things that makes this, safe, efficient, and billable is that it has to go to that beacon, because that's how we do the tracking in a way that can be done. So unless you plan, and the beacon for a large scale solar project is about the size of a shipping container. So we could warm your wedding. It'll cost you, $50,000 to $100,000 an hour. And we have to put a shipping container in your backyard. And everyone in a 1 to 2 mile radius is also getting warm. So
yeah.
Maybe. Well, it depends. How much is your wedding worth?
Yeah. The crop, I guess where I'm going with this is that I would think this on-demand spot warming, it at super scale, it starts to approach this realm of geoengineering almost. I know that's not the application, that's not the focus, but
well, I would caveat it this way: is turning electricity into heat is 100% efficient. So wouldn't it be better to just heat your backyard and not the surrounding town and take the electricity from a solar project a few miles away that we're illuminating at night?
Yeah, totally.
This is one of the reasons why mirrors from space have some issues, is oh yeah, you could supply light. It's but you're supplying it to the entire town, not to that one thing you might want light on. It's you're competing with LEDs on a stick with some batteries. So this is the warming thing, unfortunately falls into kind of the same thing where and this is almost kind of the big thing of overview is what you want to do is use the energy where you want to use it, not everywhere else. You want to produce it where you want to use it. You want to get it there, and you don't want it everywhere else. Like, think about it like from light pollution. Like, light pollution is because you're illuminating stuff that doesn't need to be illuminated. It's like why we're getting better, downward facing light bulbs for streetlights. So it only illuminates right there and doesn't shine the light into the sky for it to be scattered and bother people. So the whole thing here is, can you make your big areas you need for generating the energy in a place where it doesn't matter, like in deep space, okay, in geosynchronous orbit, where you can put up many square kilometers, a few thousand square meters at a time, up in space, where it doesn't affect these things, but then concentrate the energy. Like, the whole of humanity has always been taking diffuse energy and using it in a concentrated way. Like, this is how food works. Like, us, you have a square kilometer of crops to feed, not a square kilometer of people. So all of humanity has always been about taking diffuse energy sources and concentrating them. So that kind of heating and illumination thing, like, you don't want to heat and illuminate the things that aren't useful. It's a waste of energy as opposed to getting the kind of concentration. So overview is all about concentrating both spatially and temporally the use of that energy from an area where large areas are easy and low cost. Like, space costs you mass, like the cost is mass, not area. Okay. And a real cool thing to think about is if you hold your arm up and your palm up at like arm's length, your hand at the distance of geo is about the size of North America. Okay. So like that small fraction of sky is actually an enormous amount of area intercepting sunlight. Okay?
I see what you're saying. Yes.
So like, if you imagine for us, like, okay, let's say we put up 10,000 satellites into that space. Okay. Those satellites are about 100, or what does that work out to be? About 20 miles apart. Like, if you put 10,000 of them into that space. So like, quote Douglas Adams, like, space is big, really, really big. So if you have these large area things, put them there. Okay. Where the energy is, but the utility of that energy is where it's demanded. It's the people, it's, the stuff on the ground, it's cities, it's all those kinds of things. We need the energy there, and we need it in a efficient, concentrated way. And space solar energy solves that problem.
Totally. Yes. And this is why I love this so much. It's like, you have elegant engineering design solutions to things that kind of, they hit multiple things at once, but then it also solves this super giant big picture problem, like Elon just said at WEF, which was like, all the power is in space, right? All the power is in space. All the demand is on the ground. So the AI satellite thing, it's like, okay, we could put that because you can just beam bits up and down, but like, we need to manufacture stuff. We need to like power homes. Like, we're not living in space. We're not, you know what I mean? So
yeah.
The
way I think about it is like, first of all, like, GPU generations are not that long. So it's like, why are you putting them up in space if you have to refresh it all so often? Like, the energy's in space. The fact that we're looking at doing that should tell you, one, the grid is broken.
Yeah.
Two, people believe that we can get stuff into space cheaply. And three, that thing you're getting into space cheaply is huge areas of solar panel. So I like to look at AI power demands as the canary in the coal mine. Like, what AI has done is reveal kind of how broken, not just the physical nature of the grid, but how we use it, how we deploy it, how fast can we deploy it, the economics of that. Like, there are companies out here where Meta is putting GPUs in a tent next to a solar project because getting the grid connection is orders of magnitude harder than just building a solar project, which you can go like that. You can deploy them so fast and so cheap. The issue is they only work 25% of the time. So again, it's like, if the demand is here, if the energy is there, isn't the optimum idea to bring the energy from where it is to where you need it, as opposed to, because like you can put GPUs up in space on satellites, but on the other hand, like putting, car production, putting, close to 10 billion people up in space that all need energy, like that's a much more difficult thing. Now eventually, like, I believe that we need to be a multiplanetary species. Okay. But this also works on Mars and it works everywhere else too. Like as Elon says, all the energy's in space. So, but how do we solve the 80 to 90% of demand, even in the foreseeable future, that isn't a data center? And also solve the data center problem while we're at it as well. So yeah, we really like to say like the easier way to solve that problem is to just get the energy down, because then you can use it for whatever the demand is. Like when you're done training your model, okay, now that data center is consuming 0 until the next model comes up, or you go into inference and everything like that. So but the one invariant is humans are going to need a lot more electricity in ever increasing amounts in places we don't know yet. I mean, think about it this way. Like one of the big problems with the AI thing is like, we thought all the demand was going to be in these areas at these cities and these kinds of things. And now all of a sudden it isn't. So now you have power being generated in places not where it's used. So, but 20 years from now, I can guarantee you we're going to need more electrical power. No one can predict where that's going to be. So I think the best option is to make a generation source that carries with it the ability to put it wherever it ends up being. Like say we make AI suddenly 10x more efficient from an energy basis. I mean, we'll still probably use the same amount of power because we'll just use more of it. But let's say we suddenly crack like self-replicating robots and they need massive amounts of welding and stuff like that. And, those kinds of things. Well, okay, now you have a factory. Now that needs power. Well, okay, are you going to put everything in space eventually? I mean, sure, but the predictable thing is the energy piece. So like, let's solve that with a solution that can then bring everything else along the way. Sorry for the just rant on that, but it's really all about where you put the energy.
This is exactly what I'm here for. This is awesome. Yeah. I'm curious then, another question would be like, what has been the sort of receptibility from the buyer side here? Like if you talk to solar operators, are they just all over this? Are they like, oh, this is weird or anything like that?
I mean, they like it. So I always joke that like it's one of the easiest sales pitches for the upfront part, where it's like, you have this huge existing asset that only works 25% of the time. How would you like to have it work 75% of the time without building anything new? Like, we'll do a revenue share on that. But from your point of view, it's like, okay, what's your profit margin on this? Like, now you're making power at night. The sales pitch is pretty easy. Like, you're generating electricity. How would you like to do it more with that existing asset? That's why we always talk on this about like, it's a photon market. We had one advisor say, you can think of it as fuel for solar farms. So there's already like an existing model for that. It's like, instead of selling fuel to a power plant, you're selling fuel to a power plant. It's just photon fuel for a photon power plant instead of, natural gas to a turbine. And that's kind of a good way to think about it from that kind of paradigm, is like, now, like you think about it, the power plant, that a natural gas turbine, its cost is dominated by the fuel. Okay. The turbine, and so the more energy you make, the more fuel you use, but the cost of that energy is dominated by the fuel. In this case, again, it's the same thing. It's dominated by the photon fuel, and that's the business we're in. So once we get past the kind of technical hurdles, like, okay, this sounds like science fiction, why? It rapidly turns into an economic discussion. Okay, then it's like, okay, well, how much does it cost? How are you going to get it here? Like, how do we get it? What is the down payment? All these different things. So the same journey, you and I just went over the past, a little over an hour. Is the journey that we get on with customers, where it's like, okay, this sounds like science fiction. Okay, well, here it is. We just did it from an airplane. Here's the thing. We can show you it in the lab. Like, these are off-the-shelf pieces that go into this. And then they're like, okay, well, how much does it cost? Okay, well, here's the economic models, and here's what you can do in this. And then it's like, okay, well, how much do I have to pay up front? And it's like, okay, so we're past the sale on this. We're good to go on this. And that goes for all the different kinds of customers. So like, we talk with hyperscalers, we talked with IPPs, like anyone that has solar projects or gets energy from a solar project is a customer.
Yeah. And I mean, again, zooming out, like you guys are kind of riding these like awesome economies of scale learning rates on laser diodes, on solar panels, and then now on launch as well, selling into like this absolutely constrained bottleneck market in a way that's super flexible, super dispatchable. So it's awesome. I get it. Modi engineering at its finest. So I had one last question.
Okay.
It was from one of the audience members, Scott Norman, GP at Earthrise Ventures, calling in, asked, what about the popsicles? I don't know. Is this code for something?
Yeah, it's okay. So it's a fun story about, the grittiness of startups, as well as sometimes the best engineering solution isn't necessarily the like, neat, aerospace-y, super lightweight kind of thing. Okay. So I was once working on a project where we had to cool a big laser on an airplane. Okay. And air at high altitude is very cold. Like if you've ever flying on an airplane, you get the little, display of ambient air temperatures, 50 degrees below zero or whatever. So the air is really cold. So I had the idea of okay, well, ice is a really good phase change material in order to cool stuff. And lasers tend to operate in, near freezing point of water to, around that kind of range. So it's okay, well, let's use ice as the phase change material to absorb the heat from the laser. And then when we need to refreeze it, we just blow cold air past it, which we have in spades. So what do you want? But water expands when it freezes. So you can't just put it in a metal tube as your heat exchanger. So what you want is something that is thin, very robust, but can flex as the ice expands. Okay. And what this ends up, but since it's a lot of surface area, it doesn't have to be metal. It just has to be there. Okay. So you can use plastic. So what this ends up looking like optimally is an otter pop, like one of those plastic, squishy popsicles that you squeeze from the bottom and it comes out the top. So the place I was working at the time, I was okay, this is just a bunch of popsicles in a box that you're flowing antifreeze past in order to cool it. So I was why don't we use popsicles? They literally work for this. And they're well, this is an aerospace thing and basically all this stuff. So I ended up having to make Kapton, $1,000 a pound, distilled water aerospace popsicles for this project. Okay. Well, for our airborne test, we can't cool it with a radiator like we do in space. So we had to use a phase change material to cool a laser in an airplane. Well, we're a startup here. And also, so I was okay, we're just going to put popsicles in a box and flow the coolant past it. So on that airplane, there was literally in our cooling module associated with, we test the radiators and stuff on the ground, not for part of the airplane, but on the cooling module of that, there was literally 75 pounds of otter pops from Costco that we bought at $1 a pound or less, and flow antifreeze pass. So, it was the joke when we first were trying to figure this out, and I'm okay, so I'm CEO here. We're just going to use the regular popsicles. We're not making aerospace. And it turns out the crazy thing is the Costco popsicles perform better. Because the sugar depresses the freezing point of the water. So they actually run at -1 C instead of 0 C, and every degree matters. And the sugar provides nucleation sites, so it doesn't super cool without freezing. And so they work across the board better. And so I told Scott, he's one of our investors, I told him that story early on, and he's okay, so yeah, there's 75 pounds of popsicles. There won't be any popsicles on the spacecraft. But it was one of those great stories of how do you solve a problem the efficient, economical way, not just, because that's the way they've always done it. So there you go, popsicles for laser cooling.
That's the
Yeah, you don't want to eat them afterwards because they're covered in antifreeze. It's not a good idea. We dispose of them properly. But it's a great gritty startup kind of story.
That's awesome, man. I love it. Nature of disruption is what's the right way to actually do this, not just what's the conventional rule of thumb or whatever. I'm curious then for you guys, what's coming up next? What's kind of on the horizon? You have an audience right now. There's 1,000 people watching, and more will watch later.
So we just kicked off a fundraise for our Series A. So active investors, we're already talking to a lot, always looking for more. If this is a space that you want to get in, that's key. Contact us. It's actually looking really good. That gets us through our next big demo, which is putting up the subscale version into space. We have booked on a SpaceX shot for 2028, early 2028. I think it's Bandwagon 7. So shout out to SpaceX on that one. And so that gets us through that, plus a lot of the manufacturing. Also, if you're interested in working on this, okay, we have an unbelievable team of engineers and press people and just across the board. Look at our website. We have a bunch of job postings on there. Finding the people that, I guess the lesson I've learned over, 20 plus years in this industry is companies and projects and changing the world starts with the team. Okay. Like if you find the people that are just, that's what they want to do, they want to make that happen. Like the reason why, if you think of a company that's on the cutting edge and just making it happen, it's because the people in that company are like, okay, this is my mission now, like making this happen. If you're one of those people, you should come and work for Overview.
Hell yeah. I'm loving it. If I was still an engineer, I would be all over it. So it's awesome. That's great, dude. Awesome. Thank you for joining. Thank you for explaining this. I think I learned a lot about. I'm a convert now.
Awesome.
I'll send me a T-shirt. Send me a popsicle. You should sell. You should have a on your store merchandise.
Overview branded popsicles.
Yeah. They can be like aluminum popsicles, something like that.
Yeah. That's actually a pretty good idea. Okay, I'll talk to our branding people. Let's see if we can kick off some merch, like Overview branded popsicle.
Hell yeah. All right. Thanks, Mark. Thanks so much for joining.
I will send you a T-shirt though. Okay, cool. Thank you.
Okay, take care. All right, that was awesome. Yeah, energy is the #1 bottleneck to growth, and there's like a multi-year backlog in the grid interconnection queue, and so it's almost like we've regulated ourselves into space, but as Mark was explaining, eventually the economics tip in favor of space-based activities, ultimately to do this kind of space-time arbitrage on all the energy is in outer space and all the demand is on the planet Earth. So thanks for joining. Back tomorrow with AI-enabled CAD for mechanical engineering.